In this video, we'll finish developing our model of a rocking boat by considering how the boat's shape affects its rotational motion. Recall that in the previous video, we obtained this linear approximation for the torque exerted on the boat that is valid for small rotation angles. K is a constant that is positive if the boat has a stable equilibrium and is negative if the boat has an unstable equilibrium. We then used this expression for the torque to derive this second-order differential equation that describes the rotational motion of the boat around its equilibrium position. However, for this equation to be useful for us, we need to figure out how the constant K depends on the physical parameters that describe the shape of the boat. This is a problem in physics. We know that torques are generated by forces, and so we need to figure out the dominant forces that are acting on our boat. For simplicity, let's first consider the case when the boat is sitting flat in the water at theta equals 0. From the work of Isaac Newton, we know that the force of gravity acts on all of the pieces of mass that make up the boat. However, remember the remarkable fact you learned, that even though the force of gravity acts on all of the mass within the boat, we can treat the force of gravity as a single force which points down, which I'll label by F sub g, that acts through a single point called the center of gravity, which I'll label by C sub g. In calculus, you would have learned how to calculate the center of gravity for a body of an arbitrary shape. Now, we also observed that when the boat was sitting flat in the water, it wasn't moving up or down in the water, and so we know that the net force on the boat must be 0. Therefore, we know that there must be another force acting on the boat in the opposite direction to the force of gravity. This is the force of buoyancy. The force of buoyancy is the result of all of the pressure forces that act on the submerged surface of the boat. Just like we were able to treat the force of gravity as a single force acting through a single point, there is a theorem called Archimedes' principle which states that we can treat all of these pressure forces as a single force of buoyancy that points up, which I'll label by F sub b, and that acts through a single point called the center of buoyancy, which I'll label by C sub b. The center of buoyancy is located at the centroid of the submerged region of the boat. Unlike in the case of the center of gravity, the center of buoyancy is purely geometrical, and it does not depend on how the mass is distributed throughout the boat. As we said before, the magnitudes of the force of gravity and the force of buoyancy must be equal, because the boat is in vertical equilibrium. We can now also understand why the boat is in rotational equilibrium. This is because the force of gravity and the force of buoyancy act along a single line. Therefore, because they're acting along the same line, they cannot generate a torque. And so the torque at theta equals 0 is equal to 0. To recap, we said that the force of buoyancy can be considered to act through a single point called the center of buoyancy. And Archimedes' principle also says that the force of buoyancy always points directly up.